Testing. Testing. Part 2. Testing. Okay. Take what? I tried using fast, but it's not meeting. Okay. Okay. We're having this live. As I say, I wanted to do the final video yesterday, but there was no time. So I'm going to try to finish up everything today so that I'll have time for my personal reading. Okay, today's video, we're going to explain what gradients, the concept of gradient, divergence, and coil is. And after that, we're going to use our knowledge test to solve question 8, 9, and 10. We already have solved question 8 and 9. We're going to space and not solve question 10 using the small body who's still. But now that we're here, since there's a bigger board, we'll be able to solve question 10. Okay, let's just begin. Before we begin, let's try to brush through our knowledge of scalars and vectors. And we're also going to apply or study what a scalar field is and what a vector field is. Just brief introduction to all this. You already know the scalar is something that can be defined completely using only magnitude, such as temperature, your mass, your height, and so on and so forth. But things that are vector, they need the direction. You don't just define them using magnitude only. You need to tell me which direction is moving, and you get what I mean. Examples of vectors are acceleration, where are you accelerating to your velocity, where are you moving towards? Force, where is the force applying? Upward, parallel to the left, where is it applying? Where is the force pushing the body to? Okay, for a scalar field now, we have your coordinates, or you have an area filled with scalar points or scalar values. Let's say temperature. Let's say how to measure the temperature in the particular area, and the temperature around this area are given as such. As you can see, everything here are all magnitudes. And I give you coordinates. 1, 2, 3, 4. If I tell me the temperature at 1, E, then we go to point 1 horizontally and point A vertically, and you tell me, and your reply, the output that the function give you is 10 degrees Celsius. If I tell you the temperature at 2, C, the output to give you is 20 degrees Celsius. You can see its outputs are all scalars. So the output of or each point in a scalar field is a scalar. For vectors, each point in a vector field is a vector. So if I tell you, remember this, and I tell you at the point 1, A, what is the vector at that point? You go to 1, A, that is this point here, and the result to give you is a vector pointing towards a particular direction. Okay. Now, what do we use to analyze both the scalar field and vector field, we use the del operator. The del operator is given as such. The del operator is equal to the partial derivative with respect to x I plus the partial derivative with respect to y j plus the partial derivative with respect to z k. Now, if we want to analyze a scalar field and want to find the gradient of a scalar field, what does that imply? The gradient of a function in normal 2D graph, let's see, we have a 2D curve as such. The gradient of a 2D graph is basically, let's say, turning effect. I don't really know how to describe a gradient for you, but let's see how much rise will you get per movement along the x-axis. How is it changing with respect to time or with respect to the x-axis? Yes, how is the output y changing with respect to the change in x? That's what the gradient will give you. The same thing applies to a scalar field. How is the function changing with respect to how is the scalar function changing with respect to each axis? So let's say our scalar field is 3D, and we have a curve as such. Let's say our scalar function is 3D like this, and we have a curve like this, and I give you a point, right, to tell me what is the gradient of this scalar field. It's going to give you a skin. Don't give a skin. Let me see if I can get some diagrams of how they look. But it's easier for our brain to understand or to draw to these. But we've hardly studied 3D curves. So I give you a better diagram than the one I drew here. Yeah, something like this. I'm going to give you a skin in 3D. That's basically how this thing scalar functions are depicted in 3D. In 2D, it's still going to give you the normal type of curve that you're used to in 2D. But in 3D, it's going to give you a curve like this. Okay. So ask what's the gradient at this point? It's just this exact same thing that you already know about normal gradients for 2D. You just want to give you the line that represents how or where that function going to move towards if you're increasing your x values, or if you decide to decrease it, where it's going to move towards. Now, what tells you, like, if I tell you, okay, let me give you an example. If I say f of x and y is equal to x squared plus y squared, and ask you, okay, tell me if I increase the value of x by 1 unit and I increase the value of y by 1 unit, how would f of x change? Well, it's going to be complex for us to determine just straightforward how f of x will change. But if you break it down, first of all, increasing x by 1 unit, then that is increasing x by 1 unit, then y is going to increase. Y is going to increase, there's no going to change in y. Then you now increase x by 0 unit, you're not increasing x just means the same. Then you're going to increase y by 1 unit. I'll go over that again. If I ask you to tell me the change, how f of x and y will change, if x increases by 1 and y increases by 1, it's going to be hard for us to, if like, for example, easier, but like if it becomes more complex, it will be hard to represent it. But if you break it down, first of all, you increase x by 1, y does not change. Then you increase y by 1, and x doesn't change, there's going to be better. That's where the idea of partial derivative comes in. You partially increase x, the partial derivative of x squared with respect to x, that will give you 2x. Then you partially increase y, the partial derivative of y squared with respect to y, that will equal to 2y. So the derivative of, or the way f of x will change if you increase x and y by each by 1 unit would be 2x plus 2y. Okay. Now, why does, I don't want to go again, why does the gradient of a scalar function, why does it equal to a vector? A vector, why does it equal to a vector? How does the scalar change to a vector? We already know how vectors change to scalars. Vectors change to scalars by you have the dot product. You also have magnitude. Vectors can change to scalars using dot product and magnitude. But now, where does the idea of a scalar change to a vector come from? It does it because of if x, like a little change in x, let's say for a particular function, a little change in x creates an equivalent small change in x. And for another function, a little change in x creates a bigger change in the function. You realize that the magnitude of their derivative is different. One of them, the magnitude of the derivative is bigger than the other. The second thing is that there's a change in the x direction, there's a change in the y direction. So they're basically, you can break down the scalar into two components, the x direction and the y direction. That's where the idea of the vector comes in. If you represent that derivative using a vector, you can show which direction it changes towards and the magnitude of that change. That's the reason why the derivative of the scalar function will give you a vector instead of a scalar itself. To give you a vector. In which direction is that function increasing to, and at what size is it increasing by? It can also be negative. If it is not increasing, it can be decreasing. If it's negative, it's going to be decreasing. That's basically the idea. And if it's zero, already that function does not increase. Not increasing, it's not decreasing. And it's not going to increase or decrease if your scalar field is actually constant. You already know that the derivative of a constant is zero. If the derivative of a scalar field gives you zero, it means it does not increase, does not decrease, and that means it's also going to still be a normal constant that you know. Is that going to be constant? Or I believe that's the only, but let me just give it a sample. I believe that's the only way that the scalar, the gradient of a scalar is going to give you zero. Oh yeah, and where the field is constant in space. So I say that's the only way that we would have the gradient of a function to be zero when the field is constant in space. Okay. I believe that explains the gradient. I've covered why the gradient of a scalar gives you a vector. I've covered what the gradient of a scalar field represents. It shows you how much change the scalar field has at a particular point and what direction that change is. But mathematically, how do you get it? Well, you get it by multiplying that scalar field with nabla or del function. So you have del of f, or let's use del of phi. What does this represent mathematically? Well, you have nabla or del, we can use nabla. You have nabla, the partial derivative of the partial derivative with respect to x I plus the partial y j plus partial z k multiplied by your scalar field. If you open this bracket, you have the partial derivative of phi with respect to x I plus the partial derivative of phi with respect to y j plus the partial derivative of phi with respect to z k. This is going to be your mathematical way of representing the gradient of a scalar field. Now, if your scalar field is 2D, okay, somebody join, keep going real. Can you make Krishna? No, Krishna, is that India? Is that India? I didn't even say Indian one. No, I have Indian one. My Telegram channel, but one of my classmates was like, oh, you don't not like that's what you say. But this is the first time that okay, that's good. Thank you for learning. Okay. Well, this is the mathematical representing it. But I still want to go. Yes, you pronounced it right. I know, Krishna. I was watching Indian movies now. I've watched some Indian movies, so I know how to pronounce the Krishna. But hello, welcome to Nigerian though. Welcome to my live stream. Okay. Let me just go further. I need to explain what this. Good evening, everyone. This is the physics. Okay. I'm in physics later. Let me explain what this mathematical representation represents. So now, if we have our scalar field, we have a scalar field, something like this in 3D, though, in 3D. Let's say something like this. Okay, you would agree with me that this scalar field has, like, if you cut a strip of it along the x-axis, you will get a 2D graph. Oh my god, it's going to be very hard to explain this without all these YouTube channels. They have people that can edit videos for them, but I don't really have that. So, but let me use something that I believe we all know what if. Okay, let me use this. Okay, look at this. Let's say this is our scalar field, right? And I want to find out how this scalar field changes. It's going to be, as I said, it's going to be hard to just take it as a whole. You have to break it down. How it changes towards the x direction, how it changes towards the y direction, how it changes towards the z direction. And I want to find out how it changes towards the x direction. Then I'll cut it along how to along the x direction. Yes, I'll cut along the x axis. And what it will give me is a cross section at that point, which will give me in 2D. So from that cross section, I can now determine the gradient for the partial, like it's not going to be the full derivative of the scalar field. It's just going to be with respect to that x axis. Because I'm finding how that scalar field changes in respect to the x axis. So okay, I'm cracking. So let me confirm that the video is recording. Okay, your voice is not clear. Oh, however, you might need to change your mic or check your internet, bro. Yep. Okay. Thank you for the feedback. I'll check from here. Yeah. That's right, the audio is cracking. But I don't think there's anything I can do. That's the I can do at this point in time because I've already gone far. If I start to again, I don't think I'll start it from beginning. Oh, Mark is Let me check this. But I think it's my internet connection that's making the thing crack. But I'll just continue. Um, Hopefully, people will manage with me. In the near future, there'll be better equipment. Okay. So you want to find out how the whole scalar field is changing. I believe I've explained that. You want to find out how the whole scalar field is changing. You break it down. Yeah, first of all find out how it's changing towards the x direction. Now, if it's changing towards the x direction, then you know that it's going to have I to represent the x component. So you have the partial derivative of that scalar field with respect to that x direction I plus the partial derivative of that scalar field with respect to the y direction j plus the partial derivative of that scalar field again with respect to the z direction k. Now, in case you are a higher dimensional being that is watching this video, they are able to have the partial derivative of the scalar function with respect to whatever the fourth dimension is, a b c d e f g h I j k l. They are going to have the partial derivative of whatever the fifth dimension is, a b c d e f g h I j k l m. It keeps on going like that. But since we're 3D, we stop at just 3 I j k x y z. Okay. I believe I've done justice to explaining how this scalar field will find out how it's used, like mathematically. You will give an example at the ending. That is, I have question here from past question. I want to use that to solve for this. But I just give a brief explanation to all the concepts. So now I believe I've done that for scalar field. Let's now do it for a vector field. In the last attempt of making the video, I explained what the scalar field is, and I explained how to find the gradient. But in this attempt, I did explain both scalar and vector, and now I've explained how to find the gradient of a scalar. Now let's go on to divergence and coil of a vector. Now, if nabla multiplied with a scalar field describes for us, let me confirm that this is have been fixed. You need to understand. Let me try and fix this microphone thing. It was better than this last time. It was a lot better than this last time. I don't think it's nice to just let it be like that. Because imagine watching the video, trying to understand, and the person is sounding like Mickey Mouse. Oh my god. Six people watching now. So let me see if I can do this thing. Change the microphone. The is there a way to change the mic while the stream is ongoing? Welcome to BeLive Tutorials. In this video, you will learn how to grant permissions for BeLive to use your camera and microphone. Disable your video and mute yourself. When you connect your camera in the studio for the first time, something is way for me to do this, so I think I'm wasting post time. So I'll just continue with the audio like that. Um, Testing. So I was also like that, and I pray you will can still at least understand some things. So something like that. Though I understand actually I've confirmed the audio is actually very bad. But we pray for better instrument next time. So now we've already seen that Nabla can help us get the change of a scalar function. How does it help us get our change in a vector field? It helps us in our scalar field. How does it help us with our vector field? To help us with our scalar field, we have to multiply our scalar field or scalar function by Nabla. Now, how does this thing apply for vector? If we multiply our scalar field, our vector field with Nabla, you can do that in two ways. First of all, it can be by the dot product Nabla dot our vector field, let's say Nabla dot f, or it can be as cross product Nabla cross f. If you're using it as the dot product, then your entire result is going to give you a scalar. If you're using it as a cross product, since Nabla is a vector and f is a vector, then your result is going to be a vector. Now, what is the difference between multiplying Nabla with a vector field that gives you a scalar and multiplying with a vector field that gives you a vector? What's the difference between these two values? Well, if it gives you, if I'm multiplying using dot product and gives you a scalar, that scalar represents its divergence. And from the word divergence, the English definition that you already know, or I believe you already should know, how something is moving away from something, how it diverges. So if this scalar, if Nabla dot f is greater than 0, this implies divergence. And if Nabla dot f is less than 0, this implies convergence. If it's greater than 0, it diverges, it increases, expanding. If it's less than 0, it's converging, it's closing up. Another way, it must always be something expanding. It can also be something creating mass. If it is greater than 0, it can be creating mass, creating energy. Like, let's say you're looking at an energy field. I believe I know about force field sounds good in my head, but energy field doesn't sound so good in my head. But I'm not sure of the English name, but the English name is energy field. Let's go energy field. That's an energy field. And how much energy is being created? If it's a mass field or something like that, that's how much mass is being created at that point. It must not just be it must not be something moving away from something. It can even be your sink. It can be your sink. You know, when you water inside your sink, you are seeing your pipe here. You make that water flow into the pipe. You understand water is converging into that sink. Okay, it can be a pipe that is being out water. You can see that the water diverges away, is pouring out from the pipe. Water is being created from the tip of the pipe here. So that is what the Nabla dot f gives us. It tells us if our vector at that point is diverging or converging. Mathematically, it really is defined as Nabla dot f. But let us see if we can, let's write this down, write down. If Nabla dot f is greater than 0, is divergence. If it's less than 0, is converging. Let us see if we can simplify or expand what it is. So Nabla is the same Nabla. The partial xi plus partial y g plus partial z g times f. This f here, you can break it down again into its components. So let's do that. Let's break down f into its components. Then you have f in the x direction I plus f in the y direction j plus f in the z direction k. That is the x component of the function or of vector f, the y component of vector f, and the z component of the vector. Okay. So we're finding dot product of this with this. Now, how do you apply your dot products? Dot products are very easy to apply, and basically you multiply the I component plus you multiply the j component plus you multiply the k component. Let me just go deeper. You expand it normally algebraically. Remember, you have your partial xi times your f of x I. Then you get your partial f of x partial x. Your I cancel because I times I is 1. You can now go your partial xi times your times f of y j. I times j, or the I dot j, the dot product of I and j is 0. So this times this will be 0. I dot I dot k is 0. So this times this will be 0. That is why I write it down here. Partial yj dot f of xi will cancel out because j dot I is 0. Partial yj times f of yj would equal to plus partial f of y in the y direction. There is no j because j dot j is 1. And why j dot j 1? J dot j is 1 because of jm. A dot b is equal to the magnitude of a times magnitude of b cos theta. Okay, j dot j is magnitude of j is 1, so that is 1 times 1 cos theta. But that theta now, since j and j are parallel, yes, j and j are parallel, like the same direction. J is in the j direction, and the other j is also in the j direction. These are parallel. Then the angle between them will be 0. If they are perpendicular, the angle between them will be 90. And how that will do that is 90. If they're parallel, the angle between them will be 0. If then the other direction, the opposite direction, the angle between them will be 180. So say the angle between them is 0 degrees, cos 0 is equal to 1. So you have 1 times 1 times 1. So j dot j is equal to 1. So that's why we have 1 here. And then I don't multiply by 1 just see. So just leave that. The partial z of k times the times okay, partial of this times this because of j dot k is 0. Okay. So the partial z of k times this is 0. Partial z of k times this is 0. Because k dot I is 0 and k dot j is 0. You realize 0 because of the 90 degrees to each other, and cos 90 is 0. So it just be 0. And the partial z of k times f of z k will be plus the partial f of z with respect to the z axis. So this is what lambda dot f represents. Is equal to the partial derivative of f with respect to the x axis plus the partial derivative of f with respect to the y axis plus the partial derivative of f with respect to the z axis. Okay. Now take note, it is not the same as the that of the scalar. Because the scalar, remember, you had the vector. You have I, you have j, you have k here. And for the scalar, what you are differentiating is the same thing. The scalar function, scalar function. But for the vector own, what you are differentiating relative to x is only the x component. You are differentiating only the x component. You are differentiating only the y component. And you are differentiating only the z component. Good and fine. So I believe this explains that for the dots product of nabla and f that is like divergence. So you can write all this down if you think it's important to you. But I know it's going to be important to you, so you can write it down. Now the last part of it, let me just confirm again if the audio is recording. So I believe this explains that for the dots product of nabla and f is still bad. Okay. Let's go for vector. Let's go for the cross product. Actually, I think I forgot to actually change. You know, that time I saw that default and microphone. When I put on default, it didn't work. I don't actually do for this live stream, but when I heard OD, I was like, okay, God, I dodged it. When I was dating, I came back on me. I watched it when I started life, but stop. I want to use Google just I can change it now that life is going on. Whatever YouTube is telling me, I'm going to try setting button. Not sure this setting that is here is for the main Google, for me to set it, not for this live setting. So, but I'll just do like this. At least I'm seeing small this starting. Okay, now let's find out for the cross product. What does the cross product represent? The cross product represents the coil around. Now, okay, let me just give an example for the divergence. Apart from things moving away, things moving inside, you can also have the divergence of a function. Let's say you have plus here. This is for electrons. You can see that electrical charges, all electrical charge that's for protons. The field pushes, equally in all directions. While for the negative charges, the field are all entering inside. Yeah, so that's another way of explaining it. Yeah, now this diverges and why this converges. Okay, now let's go for the cross product, which gives us our coil. What does the coil of a vector represent? The coil of a vector basically tells us at each point what is the turning effect of that vector field. The vector field causes change. It causes change. First of all, it can cause something to increase or decrease. It can also cause something to turn. What defines a vector basically is its radius and its angle. When I was explaining normal, non-normal, when I was explaining transverse, no, not transverse. Yes, transverse and radial vectors, velocity and acceleration yesterday. I told people that the reason why you have transverse is to show you how the vector makes our radial vector to turn. That is vector makes it turn, while our radial component is telling us how much is increasing and how much is reducing. So for this one, basically, your divergence basically tells you how is the vector field is expanding or how it's decreasing, how it's shrinking or increasing. Why our coil tells us the turning effect of that vector field. So if you have a point in a vector field here, you have vectors all around it. Let's say this particular vector field has the divergence of 0. It doesn't increase, doesn't decrease. But it has a coil, it rotates. Okay. Now this is what the nabla cross F will tell us. Let me just give it a little research to know if negative answer. Obviously, I believe there's nothing mathematically drawing you or know this. Okay, if this is positive, if nabla cross F is greater than 0, then it rotates in the anti-clockwise direction. Its turning effect is in this direction. Why, if it is less than, if nabla cross F is less than 0, then it's rotating in this direction. So you can see that you need this new direction. So basically, if you know your answer will be a vector, you need direction number 1. Now, where does the magnitude come in? As a vector need magnitude and direction. So your result is giving you a vector. Where you see where the direction implies from telling you the rotation, which direction is rotating in. Now, where does the magnitude imply? The magnitude tells you how fast is rotating. How do I put this? Yeah, basically, it explains itself how fast something is rotating. Just because I'm telling you that okay, this is turning clockwise does not mean I'm telling you that me telling you that okay, this pen is rotating clockwise. I'm not telling you how fast it's rotating. I'm rotating, at 2 maybe meters per second. I'm rotating at 3 meters per second. So you need a magnitude to tell you how fast it's rotating. Okay. So like basically what that vector result gives you. That vector result, the magnitude of that vector will tell you how fast it's rotating, and the vector's direction will tell you in which direction it's rotating. So we've got our explanation on what or on why our nabla cross f, our coil vector is a vector. So let's give the mathematical expression for it. So we have nabla cross f. Nabla is the same partial xi plus partial yj plus partial z k cross another vector. Let's see, okay, let's just use f in the x direction I plus f in the y direction j plus f in the z direction k. So this is a cross product. Cross products are really large to evaluate. So most people, evaluate cross products using matrices, and I'm going to do that now. I'm going to do that when I'm solving the question. The matrix method, I previously before this for this course, I previously didn't like the matrix method because for me the matrix method was longer. I enjoyed just using this times this would be 0, this times this would be I times j. Okay, I'll explain that when I'm explaining in the factor. But what I'm trying to explain, I times this will be j. I'll put it down here. This times this, it will be minus j. Put it down here. This times this, it will be minus k. Put it down here. I just play one by one. But for this particular course, me myself, I'll strongly advise you to use the matrix method, because the matrix method, right? Even if this f of x here, you can say f of x looks small, just f of x. But let me just read the one that was inside the question. The f of x for this question is x y to the power of 3 minus y square z square. You can see that it's not just one term, it's not just f of x now. It's now a full expression. So it's going to be complex to multiply that out if you're using that method I was telling you, this times this, then this times this. So that's why the matrix method for this particular question became easier for me to apply, for me to use, than to use the previous method I was using. And the f of y is x squared plus z squared, and the f of z is minus negative x squared y z squared. So you basically understand the reason why. So the matrix method actually is more equal to what we're going to use for this. Now the matrix method represented by saying this is equal to the determinant of the matrix I, J, K. So I minus J, K. I, J, K. I minus J, K. And you have nabla x. Sorry, the partial x, partial y, partial z. You have f of x, f of y, and f of z. Then if you find the determinant of this, you will get your coil of that vector. With no further ado, with no further stress, let's now solve our questions. 49 minutes of explanation. Let's see how fast we can solve the question. Question 8. Question 8. Question 8. We have the scalar field. Okay, if phi of x, y, z is equal to x cube y z plus x y squared cube. Okay, we have x cube y z plus xy squared z cube. We should determine the gradient grad phi at the point 1, 2, 3. Okay. So grad phi at point 1, 2, 3. So let's solve. How did I define grad phi? I told you that grad phi is equal to nabla times our vector, our scalar field phi. So there's a question. why are none of the government university students watching the live? And it's normal people that are not in school that are watching it. Hello, Abilash Koneri. Please tell me if I spelled that not that right. I hope I did. Hello, Abilash Koneri. Thank you for the support. I'll definitely keep it up. But I don't know how you are understand what I'm saying when the audio is cracking like this, because I bet somebody give me feedback. Krishna gave me feedback that the audio was cracking. When I checked, it was actually cracking very, very badly, which I actually apologize. I'm deeply sorry for the bad quality of my video. But now that I've seen the importance of having a microphone, I'm actually push myself to save towards getting one. Yeah, the audio is still very bad. Testing. Yeah, it's still very bad. But we'll just manage. Thank you for the love. Okay, how do we define the grad 5? Grad 5 is defined as nabla times our scalar field 5. I told you that there's a simple way of expanding this. You can't use this to solve this per se. But after you expand, you got the partial derivative of 5 with respect to x I plus the partial derivative of 5 with respect to y g plus the partial derivative of 5 with respect to z k. I believe you can still remember that. Hope you still remember. Okay. So now to solve this, we need to first of all find the partial derivative of 5 with respect to x. Find the partial derivative of 5 with respect to y. Find the partial derivative of 5 with respect to z. And we've gotten our gradients of that scalar field. But remember, they gave us a point. Here, they gave us a point at the point 1, 2, 3. So after we find our gradient of 5, we need to now plug in those points when x equals 1. When x equals 1, when x equals when y equals 2, when z equals to 3, you need to plug in those points, and then you now get the vector that represents that gradient. Okay. So when I was using the small board, I had to break this down. I first of all found the partial derivative of 5 respect to x, partial derivative of 5 respect to y, partial derivative of 5 respect to. That was the video. The audio there was actually for me to better in a way because it was pre-recorded. So I enhanced the audio 20 times. So you can watch the video down on YouTube already. I put them down one by one. And I promised people that when I'm doing it on the board, on the bigger board, I was not going to break it down. But the way it's looking, there's still no space. I have put the whole board again. So I still think I'm going to break everything down. First of all, find partial derivative of 5 respect to x. Then find partial derivative of 5 respect to y. Then find partial derivative of 5 respect to z, one by one. So that's what I'm going to do here. Okay. The first one, we find partial derivative of 5 with respect to x. The partial derivative of 5 with respect. Oh no, you know what? I think I can clean the board up. I can clean the board up for some things. Okay. So we need to find the partial derivative of 5 with respect to x. The partial derivative of 5 with respect to x is equal to y is equal to x cubed y z plus xy squared z cubed. When you're finding the partial derivative, that constant they are differentiating with, would be the only variable. Every other variable would become a constant. Remember, when I was just explaining how we find the gradient of a scalar field, I told you that if I asked you to tell me how is this scalar field increasing or decreasing, I told you that okay, I tell you if x increases by 1 and y increases by 1, and that should tell me how that gradient, how that scalar field increased. I told you that it was going to be hard to explain it one time like I think I know that we had to break it down. First of all, find the partial derivative for only x. That is, find how x increases, then find out how y increases, then sum them together. That is the same way we're going to do it here. You are going to keep every other thing constant. Nothing changes in them. They are constant. Y does not change. Z does not change. The only thing that changes that's now partially differentiating with. So we're finding partial derivative of 5 respect to x. Y is a constant, z will be a constant, y square will be a constant, and z cube will be constant. The only thing that is allowed to change is our x. Sorry. It's like, okay, so I don't know if that should weird us out, but later out is our alphabet x. Okay. The partial derivative of 5 x. X is our only variable. If you differentiate x cube, you're going to have 3x squared. Then y and z, they are constants, so just multiply them back. Let me do that again. Remember, you are partially differentiating x cube, y, z with respect to x. Y and z are constants, so this is equal to y, z, the partial derivative of x cube with respect to x. You can just call this to y, z, the normal derivative of x cube with respect to x. The derivative of x cube with respect to x is equal to 3x squared. If you multiply everything together, you're going to have 3x squared y z. That's how we got 3x squared y z over here. So you can see how we got 3x squared y z. If you differentiate this now, remember x is our only variable. Y squared z cube is our constant. So you multiply that out first. Y squared z cube is constant. Then differentiate x with respect to x. If you differentiate x with respect to x, you're going to have 1. So this is our partial derivative of 5 with respect to x. Now let's find our partial derivative of 5 with respect to y. I would like to do this. So you can pause the live stream now and attempt it yourself. Okay, 3, 2, 1. Did you get it? Let's find out. The partial derivative of 5 with respect to y, you are keeping y as only variable, x cube and z will be constant. So you multiply that out first. X cube and z will be constant. Then you partially differentiate y, or you differentiate y with respect to y. And the derivative of y with respect to y is just 1. So you multiply this by 1 and you just have x cube z. Plus, let's differentiate xy squared z cube with respect to y. Partially differentiate with respect to y. Remember, x and z cube are a constant. So you have x and z cube are a constant. And if you partially differentiate or you differentiate y squared with respect to y, you're going to have 2y. So you're multiplying it by 2 and you're multiplying by y. So the partial derivative of 5 with respect to y is equal to x cube z plus 2x y z cube. You can see that our answers for two of them are different. This one is related to x axis, is related to the y axis. Number 3. We partially differentiate 5 with respect to z. And this is equal to, I don't use this opportunity to ask for forgiveness from those people that I promised in the last video that I'm going to do this in a straight line. And I'm still not breaking it down again. I don't want to ask for forgiveness. Please forgive me. The word is not big enough. Thank you, Namadi. So I know. Okay. If not new. Okay, you partially differentiate 5 with respect to z. You are keeping z variable and yeah, and x cube y and be our constant. So this will equal to x cube y. Partially and differentiate z with respect to z and go get 1. Plus you keep xy squared constant and differentiate z cube with respect to z. You differentiate z cube with respect to z, you're going to have 3z squared. So this will be 3z squared. So you can see partial derivative of 5 with respect to z, having x cube y plus 3xy squared z squared. Good. Now this is just the first part of our solution. Okay. Okay, this is just the first part of our solution. How many parts? Only one person viewing. Okay, this is just the thank you for viewing. This is just the first part of our solution. The second thing we need to do is to find our gradient at this point. We need to find the solution. I think this was y squared z squared. Yeah, y squared z cube. Y squared z cube. Okay. We need to find this partial derivative at this point when x is equal to 1, when y is equal to 2, and when z is equal to 3. So if you plug in those points, this will equal to 3 times 1 squared times 2 times 3. Okay, 3 times 1 squared times 2 times 3 plus y squared, that is 2 squared plus 2 squared times 3 cube. Okay, this is going to equal to 3 times 1 whole squared, that's 3 times 2, that's 6 times 2, that's 18. 2 squared, that's 4, 3 cube, that's 27. 4 times 27 is 54 times 2, 108. Okay, and this is going to equal to 126. Good. So I can clean all this up and write the partial, this is the partial of x at point 1, 2, 3 is equal to 126. Okay. For this one now, if you are plugging in those points, x equals to 1, y equals to 2, and z equals to 3, you are going to have 1 to the power of 3 times 3 plus 2 times 1 times 2 times 3 to the power of 3. So this is 1 times 3 times 3 plus 2 times 4 times 27 again. That is 108, which is all equal to 111. So I can clean all this up and just write the partial derivative, or this is the partial derivative of phi with respect to y at the point 1, 2, 3 is equal to 111. Oh. Is equal to 111. For this one, this is equal to this is equal to 1 to the power of 3 times y, that is 2, plus 3 times 2 squared times 3 squared. 1 to the power of 3, that's 1 times 2 times 2 plus 3 times 4 times 8 times 9, that is 108. 2 plus 108 is 110. Okay, so we can simplify all this and just say this implies that the partial derivative of phi with respect to z at the points 1, 2, 3 is equal to 110. Good. But this is not the final answer. Remember, the gradient of phi is equal to this partial I plus partial j plus partial z. So let's put that in. The partial derivative of phi respect to x is equal to 126. So 126 I plus the partial derivative of phi respect to y is equal to 111. So that will be 111 g plus the partial derivative of phi respect to z is 110. So that will be plus 110 k. So I believe, or not that I believe, so let's look calculated for the gradient of phi at the points 1, 2, and 3. It's going to equal to 126i plus 111j plus 110k. And that's equal to option none of the above. None of the above are correct, so our answer is E. None of the above. So this is going to be the correct answer. If you go anything other than this, then you need to go back and cross-check the work at the particular points in time. So let's see. Okay, I believe we now can move on. Let's quickly move on to the next part, question 9. If you have any questions, since you are live, you can ask questions. But those that watch this video after and you start the question, please you can send your question. You can ask me directly in case you know what I am in real life. You can ask me directly. But in case you don't know who I am in real life, you can just send your question to. You can still comment your question on the chat here and on the comment of the video. Because I also post the video. You can see put your questions on that comment there, and I'll type of questions. But in case you don't want to, to post a question, you can send your questions to 08087136012 on Telegram or WhatsApp. Also reply there, or on my email at IgweMatics@gmail.com until I make an official IgweMatics email. I'll be using my own personal email to reply those questions. Okay. So my email is AKUDUIGWEOBIDIK@gmail.com. So now let's go to the next question. I think my time is already running out. The next question tells us that if A, that's our vector A, is equal to x squared yi minus xyz g plus 2y z k. So you have x squared yi minus xyz j plus 2yz k. We should determine the divergence of A at the point 1, 2, 3. Okay. We already now define the divergence of a vector. I've explained that the divergence of a vector will never explain the divergence of f. But it doesn't matter only if you use the divergence of f or the divergence of A. A and f are just used to define a function. That's just the name of the function. So it's not really a standard that you must always use f or you must always use A. Whatever one you are given, as long as a vector, you know you are in the right track. So they can only define that. They can only say that okay, the vector is called phi. We do not come and complain to them that no, phi is a scalar. No, you use whatever you're given. If they give you the vector, they call the vector phi. You use whatever you're given because that phi is just like a place of a variable. Just like the name of a person. If I tell you, okay, the person that is meeting you today is the secretary of math department, and maybe yesterday the person that came to my meet you as secretary of math department was a man named Timothy, and today it is now a woman called Deborah that came to my meet you. You not say okay because they don't use the exact same name, Timothy. You not say okay, the person is not secretary of math department. You understand? So it's just a name given to that function. Okay. So we have the divergence of f. Oh no, sorry. Use A. The divergence of A. Okay, is equal to nabla dot A. And I simplify this. I told that nabla dot A is equal to the partial derivative of the x component with respect to x plus the partial derivative of the y component with respect to y plus the partial derivative of the z component with respect to z. So that's what I'm going to use here. This one. But this does not really help. I cannot help us solve this, but this can help us solve this. Okay. So the divergence of A is equal to the partial derivative of the x component with respect to x, the partial derivative of the y component with respect to y, plus the partial derivative of the z component with respect to z. So now what's our x component? Our x component of the vector A is going to be the coefficient of I. Basically, the function that is tagged with I, because I represents our x component. So A of x is equal to x squared y, this term here. And if you partially differentiate A of x with respect to x, the partial derivative of A of x with respect to x is going to equal to, remember, keep every other thing constant. That means in this case, y will be constant. Y will be constant. Then differentiate to x. If you differentiate to x, I'm going to have, if you differentiate x squared, you're going to have 2x. So you have 2x. So you have 2x times y. The second thing, what is A of y? A of y is equal to negative x, y, z. If you partially differentiate A of y with respect to y, you are going to have negative x, z. Because remember, negative x, z. Because remember, negative x, z is constant, but y is the variable here. And if you differentiate y with respect to y, you're going to have 1. So you have negative x, z times 1, which is just negative x, z. A of z is going to be equal to plus 2 y z plus 2 y z. That plus 2yz. Yes, plus 2yz. And you partially differentiate the z component of the vector A with respect to z. You're going to have 2y. Because remember, z is the variable, 2y is constant. So you keep 2y constant, differentiate z with respect to z, you're going to have 1. 2y times 1 is 2y. Okay. So you have partial derivative of ax versus x is 2x. So I partial blah, blah, blah. So you just sum them together. So that's equal to the divergence of a is equal to 2xy minus xz plus 2y. But remember, I gave you the point that you're finding the divergence at. We are finding that divergence at 1, 2, 3. So x is equal to 1, y is equal to 2, and z is equal to 3. If x is equal to 1, you're going to have 2 times 1 times 2 minus 1 times 2. No, sorry, minus 1 times 3. Because z is equal to 3 plus 2 times 2. So this will be equal to 2 times 1 times 2, that's 4, minus 1 times 3, that's 3, plus 2 times 2, that's 4. Okay. So if you see, I'm going to have 4 minus 3 plus 4. 4 plus 4, that's 8, minus 3, that's equal to 5. 4 plus 4, that's 8, minus 3, that's 5. We can do 4 minus 3, that's 1. And 1 plus 4, that's 5. So I divergence is equal to 5. Now I'm at the point 1, 2, 3. The vector diverges at the rate of 5. I don't really know what 5 represents. If it represents in 30 seconds, I'm not really sure. But basically, the higher number you have, the faster it diverges. The lower number you have, the slower it diverges. And if you have a negative, it's sinking inside. It's not diverging, it's converging. So at this point, now it's diverging because it's positive, but it's diverging at the rate of 5. So if you have a higher number, it diverges faster. If you have a lower number, it diverges slower. Let's go to the last part of it, coil of a vector, which for me is the biggest part. So I will have to just stand up first. The coil of a vector is very large, and that is the reason why I'm doing this video using this board. So that I'll have space to do the video. So I have space to solve. So I have space on the board to solve. Okay. Let me read the question. I think from here, still and we go for the short. Dr. Balagnet. Okay. Hopefully that whole board will be the same. So how many people are viewing? Okay, 1. Thank you for viewing. Hi. Okay. Question 10. If vector A is equal to xy cube minus y squared z squared I plus x squared plus s squared plus z squared j minus x squared y z squared k. Did that show on the board? Yes, it did. Is it showing clearly? I believe so. Let me check from here. Okay, I believe that is okay. That's much. It's small, it's so small here, but I believe it's still seeable. Okay, we're finding the coil at point 1, 2, 3. The first one to use is using two methods. First of all, my method, not my method, it's not my main method, but this method I used to use for finding cross products. Another method is, we know that now we're finding, if I look for nabla cross A, because this is our coil. Coil of vector A is equal to nabla cross A. And nabla cross A is equal to the partial x, partial x I plus partial y j plus partial z k cross. I'm going to represent this using A of x, A of y, and A of z. Of A of xi plus A of y j plus A of z k. Now, if I find cross product, you need to know that I moves to j, moves to k, and k moves back to I. So I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. Conversely, or relatively, x cross I is equal to negative k, because if you are finding the cross product of A cross B, it's going to be a vector in one direction, and B cross A is going to give you the vector in the other direction. So negative k, and k cross j is equal to negative I, and I cross k is equal to negative j. So basically, if you are negating these arrows, it's going to give you negative, but if you are following the arrows, it's going to give you positive. So now we can solve this. So this will equal to this times this. I cross I, and this is equal to 0. So you have 0. This times this will give you partial ay over partial x. I cross j is k plus partial az over partial x. I cross k is negative j. So this will be negative j. So you have partial over partial y j cross axi. J cross I is negative k. So you have negative partial ax over partial y k. Partial over partial y j cross this is going to be 0 because j cross j is 0. Partial over partial y j cross a z k is going to be positive partial az over partial y of j cross k. J cross k is I. Okay. Partial zk cross I will be j. You have plus partial ax over partial z minus partial z of k cross ayj. Will be k cross j. K cross j is negative I. So that will be negative I partial ay over partial z. Okay, so you now add the I component. I component is partial az over partial y minus partial y over partial z I plus that for j. You have partial ax over partial z negative partial az over partial x j. One thing I've noticed is when you have z and y, you have y and z. When you have x and z, you have z and x. Okay. Then you have plus that's for k partial ay over partial x negative partial ax over partial y k. So you have y and k, you have x, and when you have y and x, you have x and y. Okay, but you need to expand it like this. Don't just assume that when you have y, because you don't know which one has negative, so you have to expand it like this. So now these are our results using my method. Now let me show you how you get it using normal what do you call that thing? Matrix method. You still get the same exact same result. You still get the exact same result. But in the matrix method, you have this now equal to the determinant of I, J, J, partial X, partial Y, and partial Z. You have AX, AY, and AZ. How do you find determinant of 2 by 2 matrix? This will be equal to the first row, first column. You bring that down here. I don't really need it anymore. But copy it down, not without, you can skip back some few seconds and get it. Okay, I'm going to no comment yet. No comment, okay. So yeah, I of the matrix. Since you are picking this first column, you erase what is this partial. You erase everything in this first column and everything in the first row. Then what you will left with is partial Y, partial Z. And you have AY here and you have AZ here. Okay? Plus, negative, minus. Remember, this will be plus, minus, plus. So you have minus, partial, no, let us step by step systematically. This is what I did for this one by one. So you have J here. This is why J. Usually negative because you have plus, minus, plus. So plus times this, plus times I just add negative times J times negative J. Okay? So remember, this is the second column. You remove your second column of your first row. The second column of your first row. So you're blocking this out. And what we left here is partial X, partial Z, AX, and AZ. Okay, you can see for J you have partial X and partial Z. So that's wow, the right track. Okay, then the last one is for K. You can see it's plus K, so you have plus here. Then you have a matrix and you have K. You are removing the first row and last column. So what you left with is partial X and partial Y, EX and EY. Now the last part is find the determinant of the 2 by 2 matrix. How do you find the determinant of 2 by 2 matrix? Is the normal way. The determinant of 2 by 2 matrix is the normal standard way. Then you do this times this minus this times this. This time and this will give you partial AZ over partial Y minus partial AY over partial Z. I minus partial AZ over partial X minus partial AX over partial Z. G plus partial AY over partial X minus, remember this times this, then minus this times this. So this times this minus this times this. Partial AY over partial X minus partial AX over partial Y. G. Now if you notice, this and this are the same, this and this are the same, this and this are the same, this and this are the same. But why is it that here we have partial AZ over X and here we have partial AX over Z minus partial AZ over X? Why did they change? But basically, if you move this negative sign into the fraction, you're going to have the positive here, which is the same as this one here. And this negative times this will give you this one here. Negative times negative will give you positive. So you get this term. So they're basically the same thing. If you move this negative into the bracket, you get the exact same term. So using whatever method you prefer, the matrix one or this one I showed you first of all, whichever one you prefer, you use it and you get this one to reach here. Know that you are through half of your work. Or that you are through 1/3 of your work. Now what is the remaining 1/3? What's the remaining 2/3 of your work? Let's find that out. Let's do that now. It's going to be very hard, very hard. I don't know how people's brain work. My mind is not that strong. I can't really start, cramming all this in my head. That's why I prefer knowing how they got it. So I can do it in the example, replicate the example instead of cramming the whole formula. It's going to be very tough to cram this head. So it's better to know how you got it. So in the example, you just do the simple step and get this expression. So once I've got this expression, you now know the 6 things you're supposed to find. You're supposed to find 1, 2, 3, 4, 5, and 6. So let's find that out now. Let's start from I. Let's start from I. You have I. You're supposed to find the partial AZ over partial Y. They are showing issue. You have partial AZ over partial Y. Your AZ is equal to negative x squared y z squared. Yeah, differentiate with respect to y. So I'm going to just do that quickly. You have negative x squared z squared. You have negative x squared z squared because we are keeping y as the only variable. So you have my negative x squared z squared as our constant, and if you differentiate y squared to y, you have 1. So you have negative x squared z squared. Our number 2, but to differentiate, partially differentiate ay with respect to z. So you have ay is this. You are differentiating with respect to z. X squared is a constant. So if you differentiate constant, you're going to have 0. So you have equal to 0 plus. If you differentiate z with respect to z, you're going to have 2z. Oh my god, so that's cracking. Okay, somebody sent me a message. J baby, I'll meet you on Telegram. I'll meet you later, please. Yeah. The first lesson, I sent me some Telegram because I'll reply to this later. Okay, so you have 2z. But if you please, if you have, if you want, like it's for the live, you want me to explain something like, please send me a message directly to live chat. Because anything on Telegram, I'm going to be formatted after this live. Okay, number 3 is to find the partial derivative of ax with respect to z. This is equal to the ax is equal to xy cube negative y squared z squared with respect to z. Xy cube is a constant in this case. So all these things here will be 0. Then we have negative y squared is a constant also. Negative y squared. Then we're differentiating z squared. Z squared is equal to z squared, we have 2z. So that will be negative 2y squared z. I'll go back again. But finding the partial derivative of ax with respect to z. That's number 3. Find the partial derivative of ax with respect to z. Ax is equal to xy cube negative y squared z squared. Xy cube and negative y squared is constant. So if you differentiate xy cube with respect to z, partially differentiate with respect to z, then we have 0. If you partially differentiate negative y squared z squared with respect to z, you're going to have negative y squared, the derivative of z squared with respect to z. If you differentiate z squared with respect to z, you're going to have 2z. That's how you got this 2z here. Then remember, negative y squared is constant, so you have negative 2 times y squared times z, and negative 2y squared z. Let's move on to the next part. Let's find number 4 to 6. IP, finding the partial derivative of AZ over the partial derivative of x. So find the partial derivative of AZ with respect to x. And this is equal to AZ is equal to this. If you differentiate with respect to x, we are going to have 2x, negative 2x, negative 2x, y z squared, because y z squared are constant. Okay, for 5, we have the partial derivative of ay with respect to x, and this is equal to ay is equal to this. So if you differentiate having 2x plus 0 because z squared is constant. For number 6, we have the partial derivative of ax with respect to y, and this is equal to the partial derivative of ax with respect to y is equal to x with respect to y. Remember, x is constant here, so that will be x differentiate y cube. You have 3y squared minus y z squared is constant, so that will be z squared. Differentiate y squared, you're going to have 2y. So that will be 3x y squared minus 2y z squared. If you notice, everything here is different because they are different partial derivatives, so they have different answers. Okay. Now that I've gotten this, we can now put it into our expression. I think this is a very long process. But before putting our expression, in order not to give ourselves much work, because my have to put all these things back. Instead, what I'm going to do is I'm going to substitute first of all before I put it back. be easier if we substitute this for put it back. It will be easier for us to put it back. Because imagine putting this writing this whole thing down here again. It will be very tedious. So better I just substitute first of all. So what do I put right down here to the numbers? So let's substitute. They said at point when x is equal to 1, y is equal to 2, and z is equal to 3. If x is equal to 1, then here we have negative times 1 squared times 3 squared, which is equal to negative 9. So here we have negative 9. I hope I did the correct thing. I really hope. AZY, plus y, you have negative x squared, z squared. Yes, negative 9. This doesn't confirm with me. So here we have 2z. Z is equal to 3. Here we have 6. Here we have negative 2 times y squared z. So that's negative 2 times y squared. The y squared is 2 squared times z. Z is 3. So that will be negative 8 times 3, that's negative 24. Negative 24. Okay. Here we have negative 2 times x is 1 times y is 2 times z squared, that is 9. So that will be negative 4, that's negative 36. Negative 36. Any message? No. Now 2x is 2x, so 2 times 1, that's 2. Here we have 3 times 1 times 2 squared, negative 2 times 2 times 9. Now 3 times 4, that's 12, minus 36. That's equal to negative 24. Okay, negative 24. Negative 24. Now we can now substitute. I know that our work is easier. Now that I've done fast, I can now sit down. Ooh, thank you, Lord. So we have now substitute back. We have the partial derivative of AZ in respect to y. The first term, that is negative 9 minus partial derivative of AY is equal to Z, that is 6. Negative 9 minus 6i, okay, plus AX respect to Z, that is negative 24. Negative 24 minus AZ respect to X, that is negative 36. So negative 30 minus 36. Negative 24 minus 36. Minus times minus is equal to plus. So here we have plus. Let me just write down so that I will not take too much space. Plus 36 plus AY respect to X, you have 2. Minus AX respect to Y, you have negative 24. Negative and negative plus 24. This K, this G. You do the remaining part of the mass. Minus 9 minus 6, that is minus 15. I minus 24 plus 36, that is plus 12. G. 2 plus 24, that is plus 26. G. This is our answer. The coil of the vector A is equal to negative 15i plus 12j plus 26k. Now, which also is quite wrong thing. This is option 15i plus 12 plus 12j plus 26k. That's option B. 15i plus 12j plus 26k. I'm not sure how clear my camera is or on which pixel you're watching this video on, but I'm very sure if all things being favorable, you'll be able to see this question. Okay. That's question 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B. Okay, that's negative 15i, so we're correct. That's how you solve this. So it's a very tedious process, but you can go to God that you are a very smart student also. It's a tedious process, but you're also a very smart student. So you can handle this, your lecturers can handle this, you can handle this. Okay, your brother can handle this. I'm lying, but oh my God. Yeah. We've come to the end of this live stream. I hope you've learned something. I hope you've done good. Thank you for watching. If you have any question, please ask. It's dark outside. Yeah. So I believe that the end of all this. And also, in case you want to buy from me microphone, Please buy. It's going to be a very, very, very good improvement for me. And I'll be so happy. I'll be so happy. Also, in case you want to buy from me board, buy. Yeah, just buy everything for me. Yes. Mwah, buy from me everything. So, thank you for watching this live. I'm seeing you next one. Let me read back to stay now. I'm so happy. Fatu. And I just want time live. And I just make noise, so you can just go off live now because I'm just easy live because I don't think I'm going to say anything important in that part. But this guy, thank you for everybody. Bye bye. Oh, I'll just let people see me now. Show some. I'll leave the jacket here because I'm not stop doing anything in still. The only thing I'll be doing here is going to be live and it's going to be in this place. So I'll just leave the jacket here. I'll take it back. Yeah. Because I'm already using coconut 24. Honestly, before like this was Mr. Fashion that I did work, but I don't think to stain the board. We try and it's hard to finish. So I'm just cleaning it now. If you have any question, you can ask when I'm trickling on. I can answer your question. How long is this thing, sir? Okay, well, not use 2 hours. Yeah. I don't know those things, not this time. But that's okay. Okay, I also leave this here. Oh, that is tomorrow. My bedroom. My cousin always have it. So the question can take it to hostel. Come to here. My tablet I'm taking with me. I forgot to do somewhere. Okay. Yes, sir. Are you doing now? Because I was also reading. Okay, I'm close to this window. I never actually that this place was little. Right, sir. Right, sir. Good, sir. Right, sir. Sir.
Successful.
Amen, sir.
Great successful.
Amen, sir. Thank you, sir. Amen. Thank you, sir.
Igwe.
Thank you, sir.